Summer 2022 was filled with a number of highs, like high temperatures, high drought indexes, high grocery costs, and high transportation costs. High electricity costs can also be added to the list, sometimes even after consumers took efforts to conserve energy. Naturally, many people want to know the cause behind increasing electricity costs for summer usage. The summer spike in energy cost adjustment, or ECA, was directly related to the cost of natural gas, a key driver for the cost of energy purchased from the Southwest Power Pool's integrated marketplace. Corey Linville, Sunflower's Vice President of Power Supply and Delivery, is here to explain the answers to some of the questions electric consumers have had.
How does SPP use this submitted cost information to determine which units to run and the associated market cost of energy?
SPP determines which units to run through a general process of stacking the resources from least expensive to most expensive, and then determining how far up that stack they have to go to serve the amount of load during a given period of time. The chart you're looking at now is the stack of the resources in SPP. The stack goes from left to right in terms of least expensive to most expensive resources. The chart also incorporates the capacity of those resources on a cumulative basis across the x-axis. So for example, if you look at the least expensive resources, those are going to be wind, solar, and hydro, included in the green portion of the graph. On a combined basis, if all those resources are 100% available and producing at 100% output, they're capable of about 30,000 megawatt hours of energy production. Going further up the stack, you'll see a nuclear component, a blue component that's primarily coal-fired resources, and then a red shaded region that's primarily natural gas-fired resources. Over the summer, SPP typically peaked somewhere around 50,000 megawatts or 50 gigawatts on a daily basis. At a load of 50 gigawatts, assuming that all resources are available, you can see that going up the stack, you get to a coal-fired resource that's producing the last megawatt hour of energy. The cost of that resource is about $25 per megawatt hour. So in terms of determining the market price of energy at any given period of time, there are three components associated with locational marginal prices. There's the marginal cost of energy, the marginal cost of congestion, and the marginal cost of losses. For purposes of this exercise today, we're going to ignore congestion and losses and just focus on the marginal cost of energy. At any given time, the marginal cost of energy across the entire SPP footprint is the same at all locations, and it's a function of the resource that's serving the last megawatt of load for that given time period. So in this example, at a 50 gigawatt load, the resource serving the last megawatt energy up the stack has a production cost of $25 per megawatt hour, and that $25 price represents the marginal cost of energy for that period of time. The resource stack we're looking at, as I mentioned, assumes that all resources are 100% available and operating at 100% output. It also assumes a natural gas price of $4 per MMBTU. What happens if the natural gas price goes from $4 to $9? In this chart, you'll see that the increase to $9 results in an increase in the production cost of the units in the red portion of the stack. Because we've assumed that all the wind, nuclear, and coal resources are 100% available at a 50 gigawatt load, we don't rely on very much natural gas. So the natural gas price increase doesn't have a significant impact on the marginal cost of energy for that period of time. However, the assumption that all resources are 100% available and operating at 100% output is not realistic. At any given time, there are several resources that are going to be unavailable due to outages, and at any given time, we all know that the wind may or may not be blowing. When wind output drops, that shifts the entire stack, and then we begin to rely on more expensive resources to the top of the stack. In this chart, we've continued to assume the $9 per MMBtu natural gas price, and we've adjusted our assumption on wind availability from 100% to 25%. You can see that that causes us now to rely on natural gas generation to serve our last megawatt of load at a 50 gigawatt overall load, and the marginal cost of energy associated with that resource serving the last megawatt hour of load is $94. So the market price of energy went from $25 in our previous example to $94 per megawatt hour, primarily associated with reduced wind output and high natural gas price.